Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list published on November 20th, 2025, about 2 days ago. It introduces MiMo-Embodied, the first cross-embodied foundation model that unifies autonomous driving and embodied AI, reaching state-of-the-art results on 17 embodied AI benchmarks and 12 autonomous driving benchmarks. The paper is titled MiMo-Embodied, X-Embodied Foundation Model Technical Report. And as we will see later, the unified training strategy and the gains from cross-domain transfer are quite striking. Also, the author shared an implementation on GitHub. You'll find a concise README describing MiMo-Embodied's capabilities, a Python inference script to run the model, and a requirements file to set up the environment, plus links out to the 7B checkpoint and technical report so you can reproduce their evaluations. On Hugging Face, you'll find the MiMo-Embodied 7B model, about 8 billion parameters, plus example notebooks for image-to-text, planning, and autonomous driving scenarios. Figure 1 makes the core claim very concrete. The orange MiMo-Embodied contour sits outside the other models on almost every benchmark axis, which means it scores higher across tasks. The left radar plot covers embodied AI benchmarks, such as task planning and spatial understanding. The right radar plot covers autonomous driving benchmarks, like perception and driving action. Together, these plots show that one unified model can outperform both specialized open models and powerful closed models in their own domains. Figure 2 highlights that MiMo-Embodied is designed as one brain for two worlds, driving and embodied robots, by organizing all tasks into 6 shared capabilities. The central wheel groups these into perception, prediction, and planning for driving, plus affordance, task planning, and spatial understanding for embodied AI. Affordance here means recognizing what actions are possible with each object, like whether a cup can be grasped or poured. The driving example panels on the left show questions about trajectories, car counts, and traffic status, while the panels on the right show embodied scenes where the model reasons about tools, free space, and object locations. Figure 3 explains how MiMo-Embodied processes words and pixels through one shared brain for both robots and cars. The top pipeline shows tokens flowing from the tokenizer through a vision transformer with a projector into the MiMo-Embodied language model, which produces a reasoning trace and a final answer. On the left, the embodied AI block illustrates single images, multi-images, and video from indoor tasks. On the right, the autonomous driving block mirrors that structure with road scenes, so the same architecture handles both domains with identical input formats. Figure 4 shows how the training data balances general vision tasks with embodied and driving experiences, which matters because that mix teaches one model to handle both robots and cars. The central donut chart summarizes the overall dataset distribution in tokens. On the left, the embodied AI panels illustrate affordance, spatial reasoning, and high-level planning questions. On the right, the autonomous driving panels mirror that with perception, planning, and prediction tasks. Along the bottom, the general images provide broad visual grounding and question-answering examples that keep everyday understanding strong. Table 1 spells out how the 4-stage training schedule is configured, which shows that the same core architecture is tuned differently as the model gains skills. This table uses one consistent optimizer and sequence length, so the training remains stable across domains. Stage 1 uses a learning rate of about 2 × 10⁻⁶ to learn embodied abilities. Stage 2 keeps that setting while shifting the dataset toward autonomous driving. Stage 4 switches to reinforcement learning data and reduces the learning rate to about 1 × 10⁻⁶, so the policy can be refined more cautiously. Table 2 shows that MiMo-Embodied clearly leads other models on embodied affordance and planning benchmarks, so the unified training actually delivers better real-world skills. Affordance benchmarks test whether a model understands what actions objects allow, like where a robot can grasp or place something. Planning benchmarks test whether the model can turn instructions into action sequences. In the MiMo-Embodied row, scores reach the low 80s on RoboRefit and the mid-60s on Part-Afford, which sit above every open, closed, and specialized embodied model listed. MiMo-Embodied shows that one shared vision language brain can drive both cars and robots and actually outperform many specialized systems, thanks to staged training and carefully mixed data. The broader message is that cross-embodied foundation models might be the natural backbone for future interactive agents. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.